Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at biopotential electrodes. In the previous set of videos, we looked at electrode characteristics, polarizable and non-polarizable electrode. And in particular, in the last video, we looked at an example of a nearly perfectly non-polarizable electrode, which is perhaps best suited for biopotential recording applications, which is the silver chloride electrode, which happens to be a stable recording solution. So, in this video, we will look at the electrode skin interface, because this is where you are placing the electrode on the skin and you are measuring the biopotential, and this is what is of interest to us. So, the electrode skin interface essentially is a complex interface. There are many barriers. First, skin has many layers. The topmost skin layer is called as stratum corneum. Stratum corneum is a barrier. Topmost, it is essentially composed of dead skin cells. This is what gets washed away when we bath. When we shower or bath and when we scrape, these are the dead skin cells that die off, and they keep getting regenerated every few days once, perhaps every day once, they keep getting regenerated. Below the stratum corneum is a stratum granulosum, and below the stratum granulosum is a stratum germinativum. This is essentially these three essentially together form the topmost layer of the skin. Below this is the epidermis. Okay. And then you have the deeper layers of the skin. Note that there are also hair cells. There is also hair that is present. So, you can see that this is the hair cell that is there, and hair also affects recording. So, to a great extent, electrode skin interface determines or governs how good your recorded signal will be, the quality of your recorded signal, or the signal to noise ratio of your recorded signal between the electrode system and the body. So, and it turns out that this is a highly sensitive or impedance sensitive and artifact prone junctions, because it turns out that the geometry matters and the exact amount of hair and the amount of stratum corneum, all these things matter. It turns out that these layers, the topmost layers of the skin essentially presents a high impedance to the electrode. So, which is why it is not really desirable to record directly from these. So, because of the relatively high impedance provided by these electrodes, provided by these skin surfaces. And then you have another artifact that is prevalent at the interface, that is the movement artifact or the motion artifact. This motion artifact is caused due to physical shifting of the electrode. Why will this happen? Because the skin is not a rigid body but a deformable body. Depending on the mechanical configuration of the body, it is possible for the skin to be stretched or slightly compressed. Because of this situation, it is possible for the electrode to move, thus changing the electrode-electrolyte interface and the composition, thus changing the impedance and the recording characteristics. Sometimes the transient voltages that are seen due to movement artifacts are as high as 900 microvolts. Sometimes this voltage, this movement artifact voltage is comparable to the signal voltage itself. For example, EEG signal voltage only will be this much. Another problem is that a simple way to get rid of movement artifact may be to think that, well, movement artifact does not happen very fast, it is a relatively slow process. So, it is a low frequency signal. So, you could for example use a high pass filter and get rid of the movement artifact, except this will not work in signals that have significant signal power in low frequencies, at low frequencies. For example, EEG has significant power at low frequencies. So, frequency is also comparable, amplitude is also comparable, then how do you remove this movement artifact? First is you need to minimize movement artifact, ensure that movement artifact does not happen. How do you do that? You press the electrode and make sure that it does not move by using, say, a duct tape, a good surgical tape for example. But there is a disadvantage with that also, because you need to consider patient safety and comfort. Sometimes pressing it hard might be a good solution from a recording perspective, but might not be good from a patient comfort perspective. As a clinical biomedical engineer, it is important for you to design things that do not harm patients, right. So, patient comfort also needs to be considered as you are making sure that the electrode does not move. What else can we do? Another thing that can be done is to use advanced signal processing techniques that separate the source of the signals without having any idea of what the possible source can be. These are the so called blind source separation methods. This is not a topic in instrumentation, this is a topic in signal processing. These are called as the blind source separation techniques. Examples. What are some examples of blind source separation techniques? Frequently in the processing of EEG, a technique called as independent component analysis is used to do blind source separation. Check out what this is for your own understanding and learning. The other is you can use a gel as an interface solution between the electrode and the skin, which essentially balances the impedance. This is a great idea and this is quite frequently used, but the problem is you assume that the gel does not dry at all, but actually gel dries in about 4 to 6 hours, depending on whether your application is for a few minutes. For example, if you are measuring ECG, you are a typical outpatient ECG, primary care ECG, you are looking at a few minutes of recording. But in the ICU setting, or let us say you are doing a sleep study of EEG, you are studying EEG activity when the person is sleeping, you are looking at recording over a 7-8 hour window. It is possible that the electrode gel will start drying after 4 to 6 hours, thus increasing the impedance after 4 hours. So, the signal quality at the start of the recording will not be the same as the signal quality at the end of the recording, but you will assume that the signal quality is the same throughout, but this need not be the case. Another possibility is that if you use, you have to very carefully apply the signal, you have to very carefully apply the gel, you have to apply it uniformly. If you apply in an uneven manner, it is possible for the contact to happen in some points, but not happen in some other points. The other is the skin stretching that could happen depending on movements that the patient is making. This could change the potential sometimes in the order of millivolts. This essentially changes the baseline of the signal itself, right? Fundamental difference. Essentially the skin has 3 layers: epidermis, which is composed of the 3 layers that we just discussed, and then dermis, and then there is the subcutaneous tissue. The epidermis itself is composed of the 3 parts that we mentioned: stratum corneum, stratum granulosum, and the stratum germinativum. essentially the corneum is the dead cells which is highly resistive and capacitive, it has high impedance. It essentially functions like a semi-permeable membrane and creates a huge barrier for ionic flow and contributes significantly in a very big way to interface impedance. How do you overcome that? Well, the method is usually abrading the top of the skin with say emery paper, salt paper. Usually for EMG what is done is you shave the hair and then you abrade the skin with salt paper and then you apply alcohol. Many times students assume that alcohol application alone is enough to clean up and present a surface that is suitable for electrode application. Usually this is not the case. Usually you need to do skin abrasion, as in shaving, abrasion followed by alcohol. Just imagine this process. If you shave, already it is an irritating situation, shaving itself, and then you abrade with salt paper and then you apply alcohol on top of it. It is an extremely irritating, okay, not an extremely irritating, somewhat uncomfortable situation. But if you want high quality recordings, many times this is needed. So, at almost all the time what is needed, you are essentially balancing between the comfort of the patient and the quality of the signal. You need to balance the two. Sometimes it is more important for us to record the signal than to worry about the physical outer comfort of the patient, because the patient might be dying, might not even be feeling the pain, for example. Then it is okay to abrade. By the way, we need to consider other things. On whose skin you are applying this? Elderly. Skin quality and the property of the skin is different in elderly. Infants, very sensitive skin. Obese people have a lot of subcutaneous fat. This is not about discrimination of individuals based on body weight. It is about how the excess body fat essentially presents a situation in which signal quality is significantly attenuated. It is a technical topic. Same with elderly, older people, they will have more skin that is loose and not so tight, and very difficult to apply an electrode to that. Whereas in infants, if you apply the regular electrode, it might cause marks or wounds for the baby. Infants, neonates, neonates means those babies, those infants whose age is less than 4 weeks old, for example. This could cause damage to the skin for the babies. So, there are multiple considerations. You need to decide about whether this regular procedure of skin abrasion, as in shaving, skin abrasion followed by alcohol, followed by gel application and then electrode application, is the most suitable method for a given patient. So, patient comfort needs to be balanced, but at the same time you are also interested in having a high quality signal. You want to have a high quality signal. To the extent possible, you do not want to cause major discomfort to the patient. So, here we show the equivalent circuit or the electrical model of the electrode skin interface. What are the various components? First you have, it's written as EBE, it's actually EHE, it's written as EBE, it's rather EHE. This is the half cell potential of the electrode itself. This is the half cell potential of the electrode. How do you know the half cell potential of the electrode? You measure this with respect to the standard hydrogen electrode. We have seen this in the previous classes. Then you have the, which also has the parallel CD and RD. What are these? This is the impedance, electrode impedance, right, along with the gel. Then I add gel to that. Essentially gel plus any moisture that is present in the skin together, that is sweat and gel together, presents a series resistance. And then at the level of epidermis, I have a skin potential, that is the ESC, skin potential. that is the potential at the skin, and then I have the impedance offered by the skin itself. Right. This is the skin impedance. Now, remember the role of the gel, it is to match the RDCD with the RECE, that is the role of the gel. What is not considered sometimes is the potential due to the sweat glands and ducts, sebaceous glands and other such glands, the potential that is offered and the impedance that they offer. These are the other things that are not frequently considered. Then below all this, you have the resistance that is offered by the subcutaneous layers. Right. What is the method to reduce the impedance? We already saw that skin abrasion, essentially abrade, shave and then abrade with salt paper or emery paper and clean with alcohol, right, essentially reduces the impedance in a very big way, because much of the impedance comes from the stratum corneum, which is essentially composed of dead cells. You can afford to lose them, except that it is very irritating, it is very annoying for the patients. And you think that this is a permanent solution, it is not. For short term recording of a few hours, this works really well, few minutes to few hours, you know, this removal of stratum corneum by abrading works great. But it turns out that this is something that gets regenerated. In a live human, the skin gets regenerated within 24 hours or little more than 24 hours depending on the person's age and health. So then what do? Then the new stratum corneum has formed, essentially increasing the impedance, which means you will need to remove the electrode for a few minutes, apply, abrade again and then apply the electrode again. That is the solution practically. And use gel electrolytes so that you can balance the impedance between the electrode and the skin. You use an electrode gel. This is a practical solution, except you assume that it provides stable ionic contact between the electrode and the skin. You assume that this is going to be there forever, it is not going to dry forever, but that is not true. It starts drying after 4-5 hours, sometimes 6 hours, after that it starts drying. What is the solution? After 5-6 hours, you remove the gel, apply a new layer of gel and apply the electrode again. That is the solution practically. That is, in the ICU setting, in the long term monitoring setting, these are some of the practical considerations that you need to have. Then flexible strain relieved cables or wires essentially reduces mechanical disturbances or movement artifacts. This is critical, because sometimes signal of interest and movement artifacts have similar amplitude and frequency characteristics. In such cases, processing these will require very advanced signal processing techniques which may not always work. So, you need to reduce movement artifact at source. One way to do that is to use flexible cables or strain relieved cables to do that. The other is to use proper adhesion of the electrode to the skin by using tight tape. In all this essentially makes sure that the skin is, that the electrode is kept firmly in place and does not move with respect to the skin. In all this, you assume that the patient is not moving. Suppose the patient is moving and that causes a skin stretching, causing a relative movement, then the electrode will be displaced. So, one way to overcome this is to use floating electrode designs. But in all these cases, you are essentially assuming that a little bit of patient discomfort is okay. You are assuming that a little bit of patient discomfort is okay, but you need to consider patient comfort in all these cases. The other method, current upcoming methods are using micro needle electrodes, fabric electrodes or flexible electrodes, dry electrodes. These are up and coming topics for still in research stage, not yet completely applied in the clinic. Yes. So, with this we come to the end of this video. In this video, we looked in detail at the electrode skin interface. With this, we end this video. Thank you very much for your attention.